Hi, welcome to my presentation. My name is MD Yusuf Harun. I am a PhD student at Rochester Institute of Technology, Rochester, New York. Today I will present our paper, SIESTA Efficient Online Continual Learning with Sleep. This paper has been published in TMLR. Code to implement SIESTA can be found on our project website. A link to the website is given in this slide. The ability to learn tasks sequentially is crucial to the development of artificial intelligence. Continual learning enables this ability in deep neural networks and holds promise for many applications. What are the challenges in continual learning? Two long-standing challenges of continual learning research are catastrophic forgetting and learning efficiency. Catastrophic forgetting has been the central focus in continual learning literature. We know that deep neural networks tend to forget previously learned knowledge while learning new tasks from a non-stationary data distribution. Another goal of continual learning is to learn efficiently over time without increasing compute and memory requirements. Surprisingly, most of the prior research solely focused on catastrophic forgetting and overlooked efficiency aspect of continual learning. In this work, we address both aspects and attempt to align continual learning with real-world applications. Another important property of an ideal continual learner is its ability to work well with arbitrary data orderings, since the data orderings in real-world setting can vary widely. In this context of data ordering, there are two extremes. First, class incremental learning, where samples arrive in batches, where each batch contains classes that are only within that batch, and classes seen in the past can be revisited. Second, independent and identically distributed or IID setting, where samples arrive in batches where there is no class boundary, meaning that data are shuffled and classes seen in the past can be revisited in future. However, in real-world setting, both data orderings are adversarial edge cases. The real-world data distribution is unknown and can be anything. Therefore, it is important to ensure that a continual learning system is robust to any arbitrary data ordering. However, many existing continual learning methods are tailored for only class incremental learning. In contrast, our method SIESTA works equally well across various data distributions. There are two extreme frameworks for continual learning. At one extreme is class incremental batch learning, where the agent receives a batch and has as much time as necessary to loop over that batch before proceeding to the next batch. At the other extreme is online learning, where the agent receives one input at a time that must be immediately learned. Humans and animals learn in a manner that is a compromise between these two extremes. They acquire new experiences in an online manner, and these experiences are consolidated offline during sleep. This motivated us to propose a new paradigm combining class incremental batch learning and online learning, which we named Online Updates with Offline Consolidation. Although this paradigm is virtually universal among animals, it has rarely been studied as a paradigm in continual learning. In this work, we formalize this paradigm for continual learning and we describe an algorithm with these abilities which we call SIESTA. Our paradigm with sleep holds promise for a wide range of real-world applications. In general, it enables efficient updating of deep neural networks. Furthermore, our paradigm matches a real-world need, on-device continual learning. For example, VR/AR headsets, home robots, smart appliances, and smartphones need to learn about the environments and the preferences of the users. In all of these examples, learning online is needed, but there are large periods of time where offline memory consolidation is possible. For example, while the mobile device is being charged or its owner is asleep. Now I'll go over the current limitation of existing continual learning algorithms. First, ability to scale. Most of the current continual learning methods validate the model's efficacy on toy datasets. For example, split MNIST and split CIFAR. It is unknown whether they will effectively generalize to other larger and more challenging datasets such as ImageNet. Besides that, problem settings make unrealistic assumptions such as particular data ordering, using task labels, and using large batches of data. These assumptions are violated in many realistic scenarios. In a real-world scenario, a learner has to learn from a large data stream, ideally never-ending. So testing ability to scale is essential to match real-world needs. Another limitation is computational cost. Training existing methods is expensive, which limits their utility for practical applications. In many cases, there is no comparison between a continual learner and a batch learner that is trained from scratch with full access to the dataset. We would expect continual learning to provide computational advantages over traditional batch learning. The efficacy of existing methods depend on extensive training. Many works use unbounded compute and do not consider training time or compute overhead as a metric to compare against different methods. In another paper published in the CVPR CL Vision workshop, we showed that many popular continual learning algorithms require more compute than traditional batch learning from scratch. This defeats the objective of continual learning, which should provide computational benefits over regular batch learning. As shown in this figure, many methods require more network updates than the regular batch learner, which acts as a soft upper bound for continual learners to match performance. In contrast, a small number of methods, including our method SIESTA, require less compute than the offline batch learner. SIESTA shows an ideal trend which is requiring fewer network updates to match batch learners' performance. Another important limitation of existing methods is the emphasis on memory or storage constraint. While this memory constraint is essential for certain applications, compute constraint deserves more attention due to practical reasons. The cost of training deep neural networks largely depends on compute rather than memory. In the next slide, I will briefly describe that. It turns out that computational expenses significantly exceed storage expenses. For example, in this table, we see that the storage cost of a large dataset YFCC consisting of 100 million samples dramatically declined over the years. In 2017, the storage cost was reduced to $87, whereas training an experience replay model on a subset of YFCC costs $2,000. It is evident that compute cost is significantly higher than storage cost. A similar comparison can be made for the ImageNet dataset. The cost of storing full ImageNet 1000 is only 66 cents, less than a dollar. In contrast, 1 million training updates on the same dataset require about $500. Keeping this in mind, we aim to make our model SIESTA computationally efficient so that it requires less compute to train. Here we list the important features of an ideal continual learner. It should provide computational benefits while mitigating catastrophic forgetting. It should show ability to scale. It should match the performance of regular batch learner. It should work well with any arbitrary data ordering, and it should be robust to the batch size. We demonstrate that our method SIESTA achieves this criteria. Now I will turn to the motivations for SIESTA. Here we ask the questions, how do humans and animals learn? According to the neuroscience, there is an interplay between hippocampus and neocortex. Humans and animals compress episodic memories in hippocampus for fast learning during wake time. During sleep, they consolidate recent wake memories to neocortex by slow learning of structured knowledge. SIESTA is motivated by the hippocampal indexing theory and latent rehearsal. For this, we take inspiration from a paper, Remind Your Neural Network to Prevent Catastrophic Forgetting. Many prior works are based on veridical rehearsal, where they store raw images in the rehearsal buffer to update the deep neural network. However, this approach significantly increases memory requirements and is biologically implausible. In contrast, latent rehearsal stores mid-level features to reduce memory footprint and also resembles how experiences are encoded in the human brain. In the Remind framework shown in this figure, earlier layers are kept frozen after initialization since they learn transferable representations. After passing through the earlier layers, mid-level features are stored in compressed form to enhance memory efficiency. During rehearsal, the features are reconstructed to their original form to update the top layer of the network, which are task-specific. This balances the stability-plasticity trade-off to adapt to new tasks while preserving previous knowledge. In the SIESTA framework, experiences are encoded and stored in a buffer during the wake phase, whereas latent rehearsal takes place during the sleep phase to consolidate recent experiences for long-term storage. I will discuss the mechanisms of the wake and sleep phases in the next slide. SIESTA makes the following principal innovations. First, while awake, SIESTA performs rapid online learning using a rehearsal-free, backpropagation-free, and data-driven approach. Second, while asleep, it performs latent rehearsal for memory consolidation. In this framework, sleep has a fixed length where it performs a certain number of network updates. The sleep and wake cycles alternate to accumulate knowledge over time. Now let's look at the details of the wake phase. During the wake phase, SIESTA performs online learning in a sample-by-sample manner. After receiving a sample, it extracts features using the bottom subnetwork H, consisting of earlier layers, which is acting as a universal feature extractor. The extracted features are then compressed using optimized product quantization, which is initialized with pre-training data and kept frozen afterward. The compressed features are stored in the rehearsal buffer along with the class label. If the buffer is full, then a randomly selected sample is removed from the class with the most samples, trying to maintain class balance. Among top layers, SIESTA only updates the output layer F, while keeping other layers in G frozen. SIESTA utilizes a data-driven approach to update F without any parametric updates. It aligns the output node for each new class K in the output layer F with its data distribution. To do this, the weights belonging to the class K in the network F are updated with a simple running class min using the output vector from subnetwork Z. This enables SIESTA to avoid catastrophic forgetting and permits lightweight online updates for faster learning. Finally, SIESTA makes predictions using the cosine softmax rule. During sleep, a sampler uses a rehearsal policy to choose which examples should be reconstructed from the rehearsal buffer to construct each mini-batch and perform a SGD update. We use the class balance rehearsal policy where we sample a fixed number of samples per class uniformly at random. Consequently, networks Z and F are updated with backpropagation in a supervised manner. We perform budgeted updates to plastic layers so that each sleep phase has a fixed length. Therefore, all the sleep phases are bounded by m number of network updates. M is defined as the number of samples used to compute SGD updates, and M can be controlled by the number of mini-batch updates and the number of samples per mini-batch. Sleep occurs at regular intervals and the wake-sleep cycles alternate. Now I will describe the experimental results. We asked the question, what is the impact of sleep on SIESTA's ability to learn and remember? These experiments are for class incremental learning and data augmentation is not used. First, we analyze the pre-sleep and post-sleep performance of SIESTA on ImageNet 1000. In this figure, we see that the performance of SIESTA after sleep is consistently higher than before sleep for all increments. This corroborates our hypothesis that sleep is critical for memory consolidation and it enhances continual learning. We have evaluated SIESTA on 4 widely used datasets. 2 of them are large-scale vision datasets, namely ImageNet 1000 and Places Standard 365. Both of these datasets have over 1 million high-resolution images. We also evaluated SIESTA on 2 small datasets, Cube 200 and Places 365 LT. Since real-world data distribution is often long-tailed and imbalanced, we investigate SIESTA's robustness to long-tail data distribution using Places LT dataset. Across all datasets, SIESTA significantly outperforms the state-of-the-art online learning method Remind. SIESTA achieves higher computational efficiency than Remind. When both methods are implemented on the same hardware, SIESTA learned full ImageNet 1000 4.3x faster than Remind, whereas for the Places standard dataset, SIESTA is 4.4x faster to train than Remind. Now, how does SIESTA compare with the offline batch learner? Here we compare continual learners with an offline batch learner which acts as a soft upper bound. The gap between the continual learner and upper bound indicates the forgetting, and if a continual learner matches the upper bound, there is no forgetting. All compared methods use the same network architecture, compute, and storage constraints. The batch learner is trained from scratch without any constraints. We first show results where all models omit augmentations, including the batch learner. All continual learners used a similar total number of updates. The figure shows result for class incremental learning on ImageNet 1000. We observed that existing methods perform significantly worse than the offline learner for final accuracy. In contrast, SIESTA matches the batch learner's performance for final accuracy. Thereby, SIESTA achieves zero forgetting, which is a remarkable achievement in continual learning. We also conducted a statistical test and found that there was no statistically significant difference between the prediction of SIESTA and the offline batch learner in incremental class learning settings without augmentation. Moreover, for real-world application, we cannot make assumptions about the class order distribution of the data stream. So we also compared methods in a continual IID setting. We see that in the figure when switching from IID to the class incremental learning, other methods decrease performance in the final accuracy on ImageNet 1000. In contrast, SIESTA maintains similar performance in both settings and shows robustness to data ordering. Statistical tests further confirmed that there was no significant difference among SIESTA's final accuracy for the IID and class incremental settings compared to the offline batch learner. It demonstrates that SIESTA works effectively with arbitrary data orderings. Now I will dive into training speed analysis. Here we show that SIESTA performs intensive continual representation learning by updating 98% of the network. SIESTA requires less than 2 hours to learn full ImageNet 1000 on a single A5000 NVIDIA GPU. This demonstrates that SIESTA is the fastest continual learning method, while others require many hours or even days to learn the ImageNet dataset. In this slide, we show ImageNet performance as a function of network updates in a class incremental learning setting. The y-axis shows the final ImageNet 1000 accuracy, and the x-axis denotes the number of network updates. Circle size indicates the number of network parameters. Ideally, we want to stay in the upper left corner of the figure, which indicates that continual learner achieves higher accuracy while requiring fewer network updates. And a small circle size is desirable so that we do not need to train a giant neural network. We can see that SIESTA meets this criteria, whereas other large models underperform SIESTA and require a significantly large number of network updates. This demonstrates that SIESTA is the most efficient and performant continual learner. Here we list all the methods that we compared in the paper in terms of their final ImageNet 1000 accuracy. After class incremental learning, SIESTA achieves the highest accuracy and sets a new state of the art in continual learning. In summary, SIESTA is a scalable, faster, and computationally efficient continual learning method. Our computational analysis in terms of flops showed that SIESTA achieves higher G-flops than other compared methods. In this figure, we also see that the gap in G-flops between SIESTA and other methods grows significantly, where SIESTA is much more efficient than others in large-scale dataset regime beyond ImageNet 1000. Furthermore, SIESTA is robust to data orderings. It achieves zero forgetting in augmentation-free and large-scale class incremental learning, which is a milestone in continual learning. SIESTA closely aligns with real-world applications and shows promise to be a drop-in replacement for expensive batch learning from scratch when new data arrives. It has the potential to reduce computational cost and carbon emission from training deep neural networks, thereby promoting green AI. Finally, I would like to thank the US National Science Foundation for funding our research. Thank you for your attention.